So we've talked about multiplying a scalar by a matrix, and we know that multiplying by a scalar of 1 doesn't change the value of the matrix. We've also talked about what it looks like to multiply a matrix by the zero matrix, and we know that multiplying by the zero matrix always results in the zero matrix. The zero matrix is like the idea of zero, but in matrix form. So now we want to talk about what is the idea of 1 in matrix form. Well, it's called the identity matrix, and here's what identity matrices look like. First of all, this is what we call the I2 identity matrix. This is the I3 identity matrix. This is the I4 identity matrix. And if you look at these, you'll start to see the pattern. So with the identity matrix, we always have a diagonal of ones, positive ones, moving from the upper left-hand corner down to the lower right-hand corner, and then the entire rest of the matrix is zeros. So we see those ones here in I2, the 3 ones in I3, and the 4 ones in I4. In the same way that we use a capital O to indicate the zero matrix, we always use a capital I to indicate the identity matrix, and the only reason that we subscript it with a 2 or a 3 or a 4 is to tell you the dimensions of the identity matrix. The identity matrix actually always has to be square. You'll notice here that this is a 2 by 2, this is a 3 by 3, and this is a 4 by 4. The identity matrix is always square, so when you see I2, you know that's the 2 by 2 identity matrix. It wouldn't really help us to say I sub 2 by 2 because we know the identity matrix is square, so I sub 2 gives us all the information we need to write the 2 by 2 identity matrix. Same thing with I sub 3, I sub 4. We only need to say I sub 3 to know that it's the 3 by 3. And we can have an infinitely large identity matrix. We could have I100, which would be a 100 by 100 square matrix where the positive 1 values follow this diagonal and everything else is 0. And the thing to know about the identity matrix is that when you multiply it by another matrix, it will not change the value of that other matrix in the same way that with real numbers, if I multiply 1 by a real number, let's say I multiply 1 by 3, it doesn't change the value of the 3. I still get 3. This is also commutative, so if I say 3 times 1, multiplying by 1 doesn't change the value of that 3, I'm still going to get 3. Well, the same is true for the identity matrix. So if I say I times the matrix A, I'm still going to end up with the matrix A. And if I take the matrix A and multiply it by the identity matrix I, I'm still going to end up with the matrix A. The only thing I have to remember, of course, is that my dimensions always matter with matrix multiplication. So if A is rectangular, then the dimensions of the identity matrix, if I multiply IA, are going to be different than the dimensions of the identity matrix if I multiply AI. So let's look at an example of that. Let's say that I have a rectangular matrix. We'll say 2, 1, 3, 0, 1, 1. So as you can see, we have a 2 by 3 matrix. If I multiply this by an identity matrix, I know right away that it's going to need 2 columns because the columns in my first matrix have to match the rows in my second matrix. And then I also know that the result of multiplying by the identity matrix is still going to be this original matrix 2, 1, 3, 0, 1, 1. And if I look here at the dimensions of the result, of course, are 2 by 3. So remember when we talked about dimensions, we know that these two have to match in order for the product to be defined. But then the dimensions of the result here are given by this value and this value right here. So the 3 columns in the result come from the 3 columns here, and the 2 rows in the result have to come from the rows here. So I know this has to be a 2 by 2 matrix. So this is going to be the I2 identity matrix like this. And if I actually do the multiplication, I'll see that that is true. Let's go ahead and get rid of this and do the multiplication here. So we know we're going to get a 2 by 3. But if I take the ordered pair 1, 0 in the first row and multiply it by the first column, 1 times 2 is 2, and 0 times 0 is 0. So I get 2 and 0, or 2. The first row times the second column, 1, 0 times 1, 1. 1 times 1 is 1, 0 times 1 is 0, so I get 1 and 0, or 1. And then the first row times the third column, 1, 0 times 3, 1. 1 times 3 is 3, 0 times 1 is 0, so I have 3 and 0, or 3. And then I move on to the second row of the identity matrix, so second row times first column, or 0, 1 times 2, 0. 0 times 2 is 0, 1 times 0 is 0, so I have 0 and 0 gives me 0. Second row times second column, or 0, 1 times 1, 1. So 0 times 1 is 0, 1 times 1 is 1, 0 and 1 gives me 1. And then second row times third column, 0, 1 times 3, 1. 0 times 3 is 0, 1 times 1 is 1, 0 and 1 is 1. And you can see that I get the original matrix that I started with. Now, if I do this the other way, I start with the same matrix, 2, 1, 3, 0, 1, 1. And I multiply this by the identity matrix. I know that my dimensions here are 2 by 3. So if I'm going to multiply by a matrix, I know I'm going to need 3 rows in the second matrix. So I'm going to have to use the 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then the result should be this same 2 by 3 matrix here. So I can see that my dimensions here match. That's how I got this 3 in the first place. I knew it had to be equal to this 3. And then the dimensions of the product are going to be given by 2 by 3, which makes sense because my original matrix is 2 by 3, and I don't expect the identity matrix to change the value of the original matrix. So if I say the first row by the first column, 2 times 1 is 2, 1 and 0 is 0, 3 and 0 is 0, so I have 2 plus 0, or 2. If I take the first row 2, 1, 3 by the second column 0, 1, 0, I have 2 and 0 is 0, 1 and 1 is 1, and 3 and 0 is 0. So I get 0 plus 1 plus 0, or 1. And then 2, 1, 3 times 0, 0, 1. 2 and 0 gives me 0, 1 and 0 gives me 0, 3 and 1 gives me 3. And then the second row times the first column, 0 times 1 is 0, 1 times 0 is 0, 1 times 0 is 0, I have all zeros. And then the second row, 0, 1, 1, by the second column, 0, 1, 0. 0 and 0 is 0, 1 and 1 is 1, and 1 and 0 is 0. So 1 there. And then the second row by the third column, so 0 times 0 is 0, 1 times 0 is 0, and 1 times 1 is 1. So I end up with a 1 there. And so you can see how the dimensions 2 by 3 came directly from these. And this example actually illustrates for us why the identity matrix always has to be square. If we expect that the identity matrix acts like a 1, just in matrix form, such that when we multiply by 1 or multiply 1 by something, we're not going to change the value of that something, then the identity matrix has to be square. Because up here in this first example, I started out with a 2 by 3 matrix. So looking at that matrix right there, I know that I have to have 2 columns in the first matrix, that's a given. And then because I know I'm going to get back to the original matrix, the product has to be a 2 by 3, which means that this 2 right here has to come from the number of rows in the product too. So automatically I get the 2 by 2 identity matrix. But if I multiply A by I put the identity matrix second. I start with a 2 by 3, and I know I'm going to end up with a 2 by 3. Because I have the 3 right here, I know I'm going to have 3 rows in the identity matrix. And then because my dimensions of the product are 2 by 3, this 3 tells me that I'm going to have 3 columns in the identity matrix. And so I end up with a 3 by 3 identity matrix. And no matter which matrix you start with, here we started with a matrix we called A both times. When you end up with the same matrix as a product, by definition, that's always going to result in a square identity matrix, which is why the identity matrix will always be square.